The universe is not the peaceful, starlit canvas you might imagine when you look up on a clear night. It is violent, unimaginably, ruthlessly violent. The cosmos produces events so catastrophic, so completely beyond the scale of anything we experience here on Earth, that even describing them accurately requires borrowing concepts from nightmares. Today, we are going to walk through some of the most extreme phenomena the universe has ever produced. And by the end, you will never look at the night sky quite the same way. Let us start with something that, if it happened nearby, would erase us without warning. No countdown, no headlines, no chance to prepare. A gamma-ray burst is the single most energetic explosion the universe is capable of producing, and the terrifying part is that it happens constantly. Scientists detect several of them every single day somewhere in the observable universe. They are not rare events hidden in the distant corners of existence. They are ongoing, relentless, and completely indifferent to anything in their path. A gamma-ray burst happens when a massive star, many times heavier than our own sun, exhausts its fuel and collapses. In the final fraction of a second, the core implodes into a black hole or an extremely dense remnant, and the energy released in that instant is beyond anything else the universe can produce. We are talking about more energy than our sun will output across its entire 10 billion year lifespan, and all of it is unleashed in a matter of seconds. Some bursts last less than 2 seconds, others stretch on for a few minutes. But in either case, the destruction within range is absolute. What makes gamma-ray bursts especially unsettling is the way that energy travels. It does not spray out in all directions like an ordinary explosion. It fires in focused beams along the rotational axis, two lances of pure gamma radiation punching through space at the speed of light. If one of those beams were aimed directly at Earth from a distance of a few thousand light years, the gamma radiation would strip away our ozone layer, leaving the surface bombarded by lethal ultraviolet radiation from the sun with no protection whatsoever. Some scientists believe a gamma-ray burst may have caused one of Earth's ancient mass extinction events nearly 500 million years ago. We were lucky then. We are lucky right now that none of the known candidates within range happen to be pointed at us. But the universe is old, and patience costs it nothing. Now let us talk about something that already exists in the dark between stars, closer to home in terms of the galaxy, and in some ways even harder to comprehend. A magnetar is a type of neutron star, and even by neutron star standards, it sits in a category entirely its own. To understand what makes a magnetar so extreme, you first need to appreciate how extraordinary a regular neutron star already is. When a massive star collapses at the end of its life and the implosion is not quite severe enough to form a black hole, the result is a neutron star. All that stellar mass is compressed into a sphere roughly 20 kilometers across, roughly the size of a mid-sized city, yet containing more mass than our entire sun. 1 teaspoon of neutron star material would weigh around 4 billion tons here on Earth. The surface gravity runs approximately 200 billion times stronger than what you feel standing on the ground right now. A magnetar takes every one of those numbers and pushes them further into the realm of absurdity. The magnetic field surrounding a magnetar is so powerful that it distorts the structure of atoms themselves. It does not just interfere with electronics or drag at metallic objects. It reshapes the quantum geometry of matter. If you were standing 1,500 kilometers from a magnetar, the magnetic field would kill you not through burning or tearing, but by deforming the atomic bonds that hold your body together at the molecular level. The electrons in your atoms would shift their configurations. The proteins in your cells would be destroyed at scales smaller than chemistry can easily describe. You would not even register what was happening because it would be complete before any signal could travel to your brain. Magnetars also occasionally release what are called starquakes. The crust of a magnetar is under enormous tension from its own magnetic field, and when that crust cracks, the energy delivered in a fraction of a second rivals what our sun produces across tens of thousands of years. In 2004, a magnetar roughly 50,000 light-years away experienced one of these events. The resulting burst was powerful enough to affect satellites in Earth orbit and briefly ionize the upper atmosphere. 50,000 light-years, and it still reached us with enough force to disturb instruments around our own planet. That single fact has never fully left the minds of the researchers who recorded it. Quasars operate on a scale that makes even magnetars feel local. A quasar is what forms when a supermassive black hole at the center of a galaxy is actively consuming vast quantities of matter. The infalling material does not drop straight in. It accumulates into a spinning disk around the black hole, heating through friction and magnetic forces until it reaches temperatures in the billions of degrees. The energy radiated from this process is simply incomprehensible. A single quasar can outshine the combined light of every star in a trillion ordinary galaxies. Not a billion, a trillion. Some quasars also generate relativistic jets, streams of particles and radiation fired from the poles of the system at nearly the speed of light, extending for millions of light years in each direction. If Earth sat in the path of one of those jets, no force in nature would offer protection. The electromagnetic radiation alone would sterilize the planet completely. Quasars were mostly active in the early universe, when galaxies still had enormous gas reservoirs for their central black holes to consume. The supermassive black hole at the center of our own Milky Way is relatively quiet today. But it was not always this way, and it will not stay this calm indefinitely. When two neutron stars find each other and begin drawing closer through the slow radiation of gravitational waves, the process takes millions of years. Orbit by orbit, they spiral inward, bleeding energy into the fabric of space itself until inevitably they collide. The event is called a kilonova. The collision unleashes gravitational waves powerful enough to ripple the geometry of spacetime across billions of light years. We detected exactly this kind of event in 2017, and the waves passed through Earth like a gentle tremor in the underlying structure of reality. But near the collision site itself, the violence is total. The explosion forges elements heavier than iron through a process called rapid neutron capture, building gold, platinum, and uranium in the chaos of two dying stars destroying one another. Every atom of gold that has ever existed on Earth was created in an event exactly like this, scattered across the galaxy long before our sun was born, eventually swept up into the cloud that became our solar system. The universe builds through destruction. Every catastrophic event out in the dark is also a kind of forge. The same explosion that would vaporize a solar system is the process by which the raw materials for new solar systems are assembled and distributed. Supernova scatter carbon, oxygen, and iron across vast stretches of space. Kilonovae spread the heavy elements. Even the furious output of a quasar in the early universe shaped which regions of its host galaxy could form stars, and which were scoured clean by radiation pressure. There is something genuinely difficult to hold in your mind when you sit with these scales long enough. The universe is not a backdrop against which interesting things occasionally occur. The universe is the interesting thing. It is a system of almost inconceivable violence and intricacy. And the brief, fragile pocket of stability we inhabit is borrowed time on a ledger that always, eventually, comes due. We exist in a relatively quiet corner of a relatively quiet galaxy during a relatively quiet era. That quietness is not guaranteed. It is simply where we happen to find ourselves standing while we look outward and try to make sense of what the rest of it is doing. The instruments we use to study these phenomena, radio telescopes, orbital observatories, gravitational wave detectors, are essentially humanity's attempt to take inventory of what could destroy us. And the more we look, the longer the list grows. And what the rest of it is doing is staggering, terrifying beyond any honest reckoning, but staggering all the